Welcome. We have two very interesting topics today. We're going to start from simulation. How do we bridge a simulation to reality gap? And after we're done, we'll switch to a completely different topic. How do we learn maximum entropy policies with reinforcement learning? It's just that each one of these topics can be covered in a small amount of time, so that's why we have these two topics today together. For the second topic, I've been mentioning in many lectures, and overall it's very exciting. There are very recent results, very beautiful theory, and very interesting properties of the resulting policy that I'm going to show you. But first, we're going to talk about simulation. And why simulation? Well, because all the reinforcement learning, or most of the reinforcement learning algorithms we've seen so far require many samples. Such samples are possible to acquire only in simulation. And indeed, the big breakthroughs of reinforcement learning has happened in simulators now so far, playing AlphaGo, playing Atari games, etc. All right? We have seen very limited use of reinforcement learning or model at least reinforcement learning on real robotic platforms. Okay? And more and more people believe that we do need to invest in simulation. We do need to invest on building simulators that not only are photorealistic, so the visuals are matching reality, but also the dynamics, the physics match reality. Now, no matter how much we invest on simulation, there will always be a discrepancy between simulation and reality. How can we train algorithms that we can bridge this gap? All right? There are many simulators available nowadays. Most of people use one of those. Mujoko, Bullet, Gazebo, etc. The pros of simulation, as we say, we can afford many more samples. You can also parallelize the simulated experience very easily, very cheaply. It's safety concerns. We don't want to deploy half-trained policies on real robots and let alone nearby humans, but also probably we're going to break the robot, right? If it's a half-trained policy. Same with a self-driving car. We don't want to deploy half-trained policies on a real car, so it's better to train in simulation, okay? Avoids wear and tear of the robot. I do believe that the progress, let's say, in the field will come from how good simulators we have, how good and how cheap robotic platforms we have that can, let's say, tolerate us using them many hours per day. Right now, the robots that are available, if you use them too much, they break very easily. They're very brittle, okay, which is another thing that does not facilitate training policies on them, rather than only testing policies on the robots, okay? And so far, the simulators are good at modeling rigid multi-body dynamics. Now, the cons of simulation is the fact that we cannot model the real world. The real world is very complex. There is wind, there is dust, there is a lot of things that we'll never be able to model, although requires a very big engineering effort to model, okay? And it's not just the visuals. The visuals is the easy part. The physics is the hardest part, okay? Even if you model them, you need to identify the right parameters of the coefficients of friction or inertia or whatever you're going to put in the system, okay? And as we said, both the visuals and the dynamics will always be different than the real world. And if you train policies on particular simulated environments and you just deploy it on a real robot or a real car, usually they will not work, okay? So in this lecture, we're going to see what people have done to bridge what they call the reality gap, okay? Simulation to reality. Now here is a big problem of simulators. It's very hard to model deformable objects, or at least currently it's very expensive. There are simulators that model fluids using particles, okay? And people use them and learn from them, but you know, it's a limited use right now. So there are a lot of research efforts in this topic. What I'm going to talk today is what has shown to work well so far. It's interesting that the same lecture I gave a year ago, I couldn't use more than, let's say, 10% of it, because things have changed. Things change very fast. What appears to be a good idea today is not a good idea tomorrow. The simulators change. The robots may change, become cheaper. So there are all these factors that will, influence whether you guys are going to use real robots to train or not, and which simulator you're going to use, and whether it's a good idea or not, okay? But what has shown to work? Domain randomization has shown to work. What does this mean? It means that instead of training in a single simulation world, you just assume ensembles of simulation worlds. You vary wildly the dynamics, how heavy the object is, what is the friction, the textures of the object, you also vary them wildly. And the reason it's called randomization, other than just domain augmentation, is that these variations you're going to do, they don't even need to be realistic. Okay, they really, if a human sees them, or if a human feels them, it doesn't need to appear real to the human. It still is very useful to train your policy in them to generalize to a real world. And the idea is that with enough variability in the simulator, then the real world would just appear as one variation. Okay? So you cover the space in which your policy needs to work. Now, second good idea is the following. This was a good lecture.
Attention, please. A fire alarm is
Guys, doesn't matter. If we're not going to finish here, we're going to do this lecture on Friday.
Do not use elevators.
So what are we going to do now? We're going to stop to go away? Probably, yes. Okay, very careful. Everybody use staircase. Don't use elevators, obviously.
Do not obstruct access.
Guys, so let's continue, please. I'm going to start by presenting you some very simple ideas which work surprisingly well on real application. I think you're going to like a lot the particular papers. We said the first idea is domain randomization. Randomized textures, randomized dynamics. They don't need to feel real or look real to be useful. The second idea is don't fit pixels in the policy network you're training. Fit something higher level, like label maps. Why? Because label maps or object maps look more similar between simulation and real world as opposed to low-level textures. And we're going to see what we mean by this. Similarly, in your policy network, don't try to predict low-level torques or low-level steering wheel signals, because those low-level dynamics are also very dissimilar between simulation and the real world. Try to have policies predict something in a more higher level. For example, where should what should be the translation or the rotation of the end effector, okay? Or where should the car go? And then let a controller, a low-level controller trained on reality to get the robot from the initial condition to this nearby waypoint, okay? So learning should happen a little bit more high level to be able to bridge the reality gap. So let's be concrete. Here is one paper that showed, one of the first that showed how domain randomization works and is effective. Imagine you have a robot, a Baxter robot, that wants to detect the objects in front of it, okay? And you don't want to grab this real data and send them to human annotators to annotate them to train detectors, okay? What you're going to do, you're going to set up a simulation environment, like here on the left. You're going to show different objects. You're going to texture them in all crazy ways. And because you're in the simulation, you know the ground truth. You know where the objects are, and you know their segmentation. Does this make sense? That in simulation, we know the world. That's the value. We know the ground truth of the world, where every object is and where its extent. Okay. So then you're going to train a detector to detect these objects in simulation under this large variability of textures, and you're going to fire this detector in the real world, and it's going to work. Okay? Okay, does this make sense? Okay, this is for object detection, but what about a more fine-grained task? For example, pose estimation. Pose meaning what is the orientation of the object, the 3D orientation of the object. Here, the object we care about is this cuboid. Well, you can still do the same. Your goal is that you have a Baxter robot or any robot is looking at the table. In the table, you see this cube, and you want to be able to estimate its pose. And you don't want to take real images and send them to human annotators to label the pose. So you train in reality. at the cost of requiring human annotations. How can we exploit simulation to do that? Well, you're going to go in simulation and you're going to put this cube. Here is the cube. You're going to put the cube in all different orientations against random backgrounds with tons of crazy objects being around, occluding the cube to be able to handle occlusions, etc., etc. Do you see the training data? Okay, so because you're in the simulation, you know the ground truth, which means what? You know the orientation of the cube. You know the corners of the 3D cuboid. So then you can ask a network, you can train a network that takes as input the crazy image. I mean, here is not crazy, here is from the real, from the Baxter robot, and predict where the different vertices are. And you're going to have the same network, feed it simulated images, and then you're going to feed it real images, and you hope that it's going to work without any fine-tuning in the real world because you don't have any annotations. So how does it usually work? A domain randomization, you start by randomizing the domain, and then you fire your detector, and you see how well you did. And here you see that you did pretty well. And then a little bit you dim the illumination, and you see that your detector fails. So then you go back as an engineer and say, oh, I need to randomize a little bit more in my simulated environment. Does this make sense? So what does it mean randomize a little bit more? I need to change the contrast and the brightness of my data and continue training with these extra augmentations, and then hop, now once the network I trained on these crazy textures and illuminations, it works under this dimmed image without any real world fine-tuning. And what is the surprising results? That it can even detect corners of an object that did not train on. Does it make mistakes? Yes, of course it makes mistakes. Like for example here, it thinks that the corners are of different objects, so under lots of clutter, of course, it's going to fail. The previous image, if you remember, the cuboid was a little bit isolated from its surroundings. Okay, so this is an idea that is very, there's a lot of excitement about this domain randomization idea. Here is a recent paper from NVIDIA. What do self-driving cars companies care about? Well, they care to train very good car detectors, okay? And then, of course, they send tons of real data to annotators to annotate the car. But in particular, because self-driving car companies don't care just about where is the 2D box of the car, but rather the 3D bounding box, which is harder to annotate, right? Even a human can make a lot of mistakes of the exact arrangement of the 3D box. We do like to have such simulation data. So what is the idea here? The top data set is called, people in the computer vision community know it, and it's called Virtual Kitty. Kitty is a real world data set of self-driving, of scenes of a car driving around in a city. Virtual Kitty was built by engineers to be in the simulation, but to be similar to the worlds in Kitty. The idea was that you will be able to train in Virtual Kitty and do well in Kitty. And now this paper on domain randomization says, I don't want to have engineers and artists. That's the problem. You cannot use your graduate students to build a Virtual Kitty. You need to use artists that know what they're doing, okay, building the worlds and the models and everything. And they say, I'm going to give up on realism, and I'm just going to generate scenes that don't make any sense. There are cars in them with all crazy textures, all crazy backgrounds, etc. What do? They take random background images. Here you see office spaces, etc. They take different models of a car. You can find those models. There are fantastic companies nowadays that sell 3D models. That sell 3D models of cars and of tons and tons and tons of other things, because these are needed for movies. So basically, there are fantastic 3D synthetic models that you can use to train policies. These synthetic models were not designed to train policies. They're rather designed for movies, etc., just to create the visual effects for people. But you can as well take them and use them in your simulator world with physics, if you like. So here is just car detection. We just still look at training detectors and bridging the reality gap. So you put these different models in different poses, different scales, different orientations, different occlusion relationships, and you train. And the question is how well you'll do if you do this. So here is the results. If you don't have any real images to do any fine-tuning, and you just train from simulated images and then you fire on the real kitty dataset, on the real scenes, then the virtual kitty no, sorry, you always use real images. Here we compare with a baseline that only trains on real images. So the virtual kitty will do better than you. And here from left to right, we show how much real images we use to fine-tune the models, the car detectors that were trained in simulation. So you see that when we use very little real data, here 0 indeed, those that trained on the beautiful dataset virtual kitty will do better than those that train on domain randomized dataset. But as you increase the number of real images where you do fine-tuning, then eventually the domain randomization wins, okay? And the question is, can we do better than 98.5, or is there an upper limit? This is not clear, because usually to publish a paper, we just need to beat the competitor by a little bit. I'm pretty sure if you push the limits of this domain randomization, you can squeeze even bigger performance, let's say, all right? Now, the important thing here is that in this detector, when you start to fine-tune, you have pre-trained the weights, one in virtual kitty, one in this domain randomized dataset. In this other, for the red column that only uses real data, you start from random weights, okay? And then as you go, you fine-tune with more and more real images. That's it. So this is another proof that you may not need a great deal of realism to do well. Now, so far I talked about randomizing observations, images. The same holds for randomizing dynamics. What does we mean by dynamics? Well, the masses of the objects that you manipulate, or of the agents that you have to learn different policies, the frictions, etc. Here's a paper called Learning Robust Neural Network Policies Using Model and Samples that does exactly this. It considers a distribution over simulators, not a single simulator. Imagine you have an ensemble of simulators where each simulator has different masses, different frictions, different physics parameters, okay? Here, in this particular paper, we'll consider no visuals whatsoever. So we're only going to be talking about physical parameters of masses and inertias, etc. So we'll train on a distribution, and we will show that you'll do much better than if you train on a single simulator, okay? So this again shows the power of randomizing the simulator. Not only we will train on an ensemble of simulators, but we'll do hard world mining. We'll try to find the simulation model on which our policy has the lowest reward and sample it more often to make sure that our policy does well even in this hard world, okay? And second, instead of just fixing this distribution over simulators, we're also going to adapt it to come closer to reality. Two ideas. So this is not just domain randomization, but there is also this additional step of bringing the distribution of simulators closer to reality. Now, to bring them close to reality, this means that you have a chance to see some real world trajectories, okay? If you've never seen the real world, there is no way that you can adapt your distribution. The idea is that you have access now to the real world. You get some few trajectories, and these few trajectories help you to adapt the distribution over simulators. So how exactly this is done? Well, here is the objective. Inside the bracket, you have the standard maximizing of the expected discount reward objective, and we've seen in reinforcement learning. Outside, we have an expectation over simulation parameters, expectation over different simulators. So we don't care about a single world. We care about training one policy that does well in a lot of worlds. So that's the idea. The second idea is hard world model mining. We will be sampling those simulator worlds based on the performance iteratively. So we sample, and then we train a policy, then we resample, we train a policy, etc. How do we sample? Well, we'll consider the worlds for which our policy doesn't do well. And you need to understand why this is important. Hard negative mining is everywhere. even when you train object detectors, when you train your policy, etc. Why this is important? Because if you sample examples for which your policy does well already, you're not going to get any gradients. Gradients you get when you correct your policy. If your policy already knows this world and solves it very well, if you sample it, you don't gain anything, okay? So that's why hard model mining is important. Is that clear for everybody? Okay, now a detail is that we don't start by sampling difficult worlds. We sample by considering all worlds, and during training, we focus more and more on the hard ones, all right? Not to make our policy, not to find a solution if we straight away sample hard worlds. Okay, great. So this is how the algorithm works. We have an iteration. At each iteration, we sample simulation parameters, and we sample trajectories, okay? And based on those trajectories, we compute the rewards for the different worlds that we have sampled. We keep the hardest ones, and then we put here any reinforcement learning method that you want that considers also only those hard simulated worlds, okay, and trajectories of those hard simulated worlds to track gradients and update our model. You can choose your favorite RL method at that point, okay? Reinforce, actor critic, whatever you like. What does this show? So this is the Hopper. It's one of the benchmarks of OpenAI Gym. It shows that if you consider one simulation world, then your policy will have high rewards. Notice that the color denotes the reward. Dark red means you get high reward. Fade white is low reward. So you will get high reward only for a particular choice of friction and torso mass, all right, for that Hopper agent. If you do ensampling of worlds, what we said to consider a distribution, you see that you get a reward in in an area that covers wide range of torso masses as well as frictions. Now, if you do hard negative mining of those worlds, you get an even wider area, okay? That's all it shows. Now, how do we sample? So the second idea, this is so far all about randomization and hard negative mining. How do you sample from distribution? The second idea is that you can adapt this distribution over simulators to come closer to your reality. To do that, you need to have access to reality. So in particular, these trajectories there, state, action, next state, have been collected on the real world. And how do you choose which simulation environments are good and which are bad? Well, you see which of those make those trajectories highly probable, okay? So the simulations that make the real trajectories probable, and we know what is a probability of a trajectory, is a multiplication of probabilities of the individual state action transitions, all right? Then you prefer those worlds. For example, if in the simulation, I push this with a particular action, and it moves, and I have a simulation world where this is extremely heavy, so it doesn't go anywhere, then of course this trajectory is highly improbable on that simulation world, and the weight of that world will go down so that I sample worlds that are closer to my current real conditions. Okay? So far we don't have any visuals. And this is how you start from a distribution of frictions and masses, and then because you do this iteration by going the real world, the sampling trajectories and resampling the simulation parameters, essentially, eventually you get it to where the red cross is, which is your real parameters, for example. All right? That's it. And here are some more plots that show that here is when you train with a mass of 3, 6, and 9, and you test in a range of masses. Then the resulting policy will have high reward only when the mass match the training conditions. Once you train on an ensemble of worlds, it does well on the full range of torso masses, okay? And the authors note that, you know what? Yes, the policy needs to handle a much harder problem. It needs to do well under a large variability of worlds. We did not see degradation due to this hard requirement, okay? Here, next is a recent paper, which I think you're going to like a lot. Similar ideas. The question is, can I learn to drive in simulation in a way that if I deploy this policy on the real world, I will do well, without fine-tuning for now, okay? Without any fine-tuning. Now we'll combine two ideas that we mentioned that they're good. The first idea is that my policy will not be exposed to raw pixels, because I know that no matter how good the artists are, there will always be a difference in textures between simulation and the real world. And the second is that the policy will not be exposed to low-level dynamics of the car. Here is the most straightforward architecture that you can train. You take an image, convolutions, fully connected, steering wheel comes as output, okay? You can train this policy using, for example, imitation learning. Somebody is training, is driving the car in simulation, and you can train this model. The question is, does this model transfer in the real world? What do you say? This is the most straightforward thing we could do, though, right? Do you agree? So actually, one of the authors of this paper came in CMU like a couple of months ago. So if you had got the chance to go to see this robotics seminar, Friday, I think, either 2:30 or 3:30, I don't remember, then you would have the chance to know the result already. The idea is that no, this policy doesn't transfer because, as we say, the pixels are very different and the low-level controller is very different. So what he proposed is that instead of training your policy on low-level pixels, train here a segmentor that take the image, predict labels, segmentation maps. Here's your driving policy that takes those label maps and does not predict low-level controls, but rather predicts waypoints where you want your car to go, okay? And then there is this controller, which is learned or it is designed, that is really on the real car dynamics that will take the sequence of waypoints and will take the car from one waypoint to the next, okay? So then all this knowledge here can be transferred to the real world safely. Now, they didn't do that. What they did is they trained in one town and one particular weather condition. I'm not sure if the projector is good enough for you to see the difference between two towns and the two weather conditions. Yeah, it seems to me that town 2 has way more skyscrapers and the weather you can understand. It seems to me the second weather is way more rainy and wet. The question is, if you train, so we don't want to deploy the pulse on the real world, okay? How can we simulate that? Well, we're going to train a network on town 1, weather 1, and we'll see how this driving policy generalizes to town 1, weather 2, town 2, weather 2, town 2, weather 1, okay? Obviously, which of those 4 scenarios is the hardest to do well if the policy was trained on town 1, weather 1? Exactly, because both the town is different and the weather is different. And let's see the results. They have very beautiful ablations here. All those models that I'm going to show were trained on town 1, weather 1. The difference between them, and they were tested on all these 4 combinations, okay? All of them. Now the difference is that what architecture we use to train those models. Let's see. Image to control is the first architecture that we showed that takes raw pixels and predicts steering wheels, okay? Raw low-level dynamics. And is the one that, yes, if you test it on the same conditions that it was trained on, it will do really well. But on the other conditions, it's not going to do well. Do you see? Is this very clear from the result? Okay. Now, image to control plus means that you're also going to do some augmentation. What is this augmentation? Well, brightness, all this brightness changes, random cropping, etc. This is what they call augmentation. Now, image to waypoint does not predict low-level dynamics, predicts waypoints, okay? And then relies on this PID controller to take from the pair of waypoints to what should be the steering wheels that will get the car to the right place. And you see that it generalizes better than image to control. Then we have segmentation to control, which is the other way around. I predict low-level dynamics, but I take as input segmentation maps, so I don't have the problem of the pixels being different. It generalizes better. And what they call as hours is that you take both segmentations as input and predict waypoints as output, and it generalizes the best. Interestingly, here is plus DR, plus domain randomization. So you help this model by randomizing the domain like crazy, all these ideas that we described earlier, still encapsulating this policy by not allowing to see pixels and not allowing it to predict low-level dynamics helps, okay? So these are all good ideas. Yes? Yes, what do we mean by waypoint? So it's right here. Waypoint is essentially you are somewhere as a car, and I tell you go to plus 30, minus 20 in the 2D plane, and rotate in that direction. So I command you by telling you your future rotation and translation, okay? Same as if you command a robotic gripper by telling it its rotation and translation, as opposed to what torques you need to apply to get to the desired location, okay? So you have a policy operating on this higher level of abstraction, and then you have some low-level controller to take care of how do you go from one place to the next. By the way, this is a good idea. Other people have also used it for example, getting, I think now a robot to stand up. Again, in simulation, they trained in terms of waypoints, and in real time, they fine-tuned a low-level controller to take care of the dynamics of the robot on the real world. Does this make sense? So you give up on trying to model the low-level dynamics of the robotic system or of the car in simulation very well. Okay? Yes?
If I'm understanding this correctly, they're separating this into 3 modules, and they're only Sim2Real transfer the middle one, or are they like just retraining the first and the last?
I see. So we didn't discuss a lot the perception module. So the perception module is essentially a segmentor that takes as input both simulated images and real images and maps them to label maps. And you can train this. People have such label maps on real images. They have the annotated, basically. People have spent the time to annotate. So we do get such label maps on real images. Okay, we can predict them simply because people have spent time already on collecting such human annotations on real data. Now, of course, they make mistakes. And if you train your perception model with perfect label maps in simulation, still you're not going to transfer well, because you're going to have perfect label map simulation and erroneous label maps on the real world. So they train in simulation, okay, and then the perception module, yes, so that's why, so you don't use the ground truth segmentation map, you use the output of the perception model simulation. Now, on top of this, they said that they really had to do things to make those segmentation maps look more like segmentation maps you get from the real world by dropping pixels and changing the brightness, essentially to make this perception module to fail more in simulation so that you are robust to such failures once you get them in the real world. But the benefit you get by using this perception module is that we do have some labels of predicting, labels of pixels in real-world images that we have collected from humans.
Okay. But it seems like it kind of makes sense that if you make the Sim2Real transfer part smaller, then it will just generalize better, since the other parts are trained on the real world.
Yes, I don't think it's a surprising result. I think the surprising result potentially is the following, that you manually engineer what will be exposed to the policy. For example, I manually design that I'm going to label all the road pixels as road, and I'm not going to show you where is the middle line, for example. Well, maybe me as a car, I wanted to know where is the middle line as well. Do you see? So then you say, OK, maybe I'll show you also the middle line. So with this interface, the engineer decides what to divide between pixels and the labels that are going to be exposed to the later policy. And if you hide too much information, For example, if you decide that both sidewalk and road are the same label, I'm sure your policy will do worse, okay? So your labeling needs to be so that it preserves the important information necessary for learning to drive, okay? No, I don't think there is anything surprising here. Now, the interesting thing, what is the interesting thing here? These people from Intel spend a lot of effort on making this simulator. They call it Carla. So the hard part is to put effort into making a simulator that later you can use. If the simulator is available, of course this is an obvious idea. But thinking that yes, this works well, it deserves to put the effort or whatever month, the human months, to build a simulator so that I can train such a system. I think this is the important decision, as opposed to fighting with real world all the way. That's it. This is what I wanted to discuss about Sim2Real GAPA. It's an active area of research and is very hopeful. If there are no other questions, I want to discuss now about learning maximum entropy policies with reinforcement learning. Yes?
Yeah, so in the last slide, here's the hours plus model. I was wondering
What is the plus? Yeah, it's some data augmentation. They say they do this data augmentation to help essentially the perception module handle the fact that from simulated images you may, because there are just so many simulated images, you have a lot of, annotations. You'll have very good label maps. And the fact that those label maps will not be exactly the same as the real world. Maybe the real world has wider roads than all the roads that you've seen in simulation. So they had to do some data augmentation on the images, basically. Okay? Like dropping pixels, changing intensities, etc. For the perception module to see a wide variety of label maps during training. Okay? So far, we've considered policies that maximize the following objective. The expected sum of future rewards, okay? And if we have infinite time, we also put a gamma there, make sure that this sum doesn't explode. What maximum entropy reinforcement learning does, it augments this objective with the entropy of the policy. What does this mean? It means that not only I want to find policies that have high rewards, that land me on states with high rewards, I also want to find policies that land me in states where the entropy of the policy will be high. A policy has high entropy when multiple actions are possible. The uniform distribution maximizes the entropy, okay? And the point distribution, where all the mass is in one point, minimizes the entropy. So I want to find policies that land me in states where I have a wide variety of options, okay? And this should not be super surprising. We have seen in the previous, well, okay, let me just say why. Well, first of all, if you have policies that are not deterministic and you have a lot of options, potentially by sampling, during training, by sampling those options, you will explore better. Mostly because the alternative is epsilon greedy, which is pretty terrible alternative, okay? So here, if the policy tells you, oh, I like this, and I like this, then you'll be able to explore better as opposed to the epsilon grid that tells you, oh, here. So basically, epsilon grid, either you have the way to go, and all the other options are equally probable. With maximum entropy policies, you don't need epsilon grid anymore to train. You just sample from those options that you have naturally available to you because you are training a stochastic policy. Now, why is it important to have alternative ways to complete the task? This is super important for generalization. Imagine that I want to reach to a particular object, and I only learn this deterministic policy, and at test time an obstacle comes in front of me. That's it. This policy dies. While if I had learned a lot of alternative ways to reach, then I will be able to generalize better. Okay? And we'll see at the end of the lecture another super important characteristic of those stochastic policies, the policies that maximize the entropy, that they can be composed. But I'm not going to mention here. We're going to see it in a few minutes. Yes, and we said also better generalization. Now, we should not be super surprised about maximum entropy, maximizing entropy, because we've seen about the principle of maximum entropy when we discussed about inverse reinforcement learning, we said, as long as we match the expert, I don't want to overcommit to a particular policy. I want to be as random as possible. And here what we're saying is that if policies have similar rewards, I don't want to overcommit to one policy over the other. I want my policy to keep all the options open. All right? And one thing that I think is interesting is that there is an SLR paper 2017 which says that if you put the maximum entropy, it's completely irrelevant to our topic, but just to see how maximum entropy is important. If you put the maximum entropy when you train a classification, image classifier, for example, and you say, you know what, try to classify the image, but at the same try to have high entropy. Essentially, don't be super confident that there's just a chair. Then this acts as a regularizer to our network. It will be able to generalize better. So we don't want overconfident predictions, okay? So entropy comes in all possible ways. So let's look. So are we happy with the motivation or? Okay. Now I want to remind you, here we have this slide when we discussed about asynchronous advantage actor critic, okay? It was an actor critic method that was using multiple threads to collect experience and naturally explore simply because it had many different threads, and each thread was updating the queue and the policy function in a synchronous way. That's why it's called asynchronous, A3C. The synchronous version is called A2C. Now, interestingly, there is a line in the paper that says this. And this line does not even appear, essentially the content of this line does not even appear in the algorithm box because it's a hack that many people do without putting it, let's say, as, without showing it into the algorithm box. What does it say is we also found adding the entropy of the policy P to the objective improved exploration, okay? So here we have discrete actions. Our policy takes as input the image or 4 images and predicts a softmax over those actions. And they said, you know what, adding the entropy of that softmax also helped. So essentially, when you take a gradient, the gradient of your policy is not exactly like that. It reminds you, grad log P multiply with the advantage, right? So this reminds us very well of policy gradients. But rather, the policy gradient look like this. You have a reward combined with the entropy of the policy on that time step, okay? So people have used, in many occasions, entropy as a regularizer when you train a policy. Now, this is very different than what we showed in the previous. This essentially maximizes the entropy of the policy of the current time step. It doesn't lead you to find policies that will have high entropy also in future time steps, okay? So this is not maximum entropy policy. This is just a regularization for your policy not to be super deterministic. And it might be, for some of you, A3C didn't work for the manipulation project. It might be that such an entropy regularization was missing and the policy was overcommitting too early, basically, somewhere in some solution. So here is our objective. So basically my point is this objective is not similar to the hack that different papers have put so far when they take policy gradients and adding that entropy, which, by the way, this addition of that entropy term is known since 1991, as we showed in the previous line. Great. So here is an objective. And the question is, how can we optimize this objective? All right? Let's recall the Bellman diagrams. The Bellman diagrams, we're computing state action Q values, OK? And remember the dark dot was when I was taking an action. And why we have different branches coming out? Because of the dynamics from the environments, that I can be sent in S prime or a different S prime or a different S prime because the environment is not deterministic. And then I land in a state, and this is an empty white circle. And then once I land in an empty white circle, again I take actions, and I have multiple branches coming out because there are many options that I can take, many actions I can take. And why the Bellman diagrams were good, where did it help us? Well, they help us to come up with this Bellman equation to know how to add things. Essentially, to figure out what you should put on this up node, you just need to sum whatever comes down on the tree, okay? So basically, the Q of a particular state and action is the reward that you would get once you take that step. The reward, we assume, depends on the current state and action. It can also depend on the next S prime, next state, doesn't matter. Plus gamma, transition dynamics, where I'm going to land. This is the stochasticity of the environment. what action I'm going to take, my policy stochastic, where I'm going to land there, I add the Q of the resulting state and action. Okay? And we said that this is the Bellman equation for state action values. Do you agree with this? Does this remind you of something? Okay, great. So we have this recursive relationship. Okay? And the only thing I want to show is that along with those rewards of the task, now we have also the entropy. We need to add it in our equation. And this entropy term can sit on the white dot on the S prime as the entropy of the policy on that S prime step, if you like. But because we know that the entropy, the definition of an entropy of distribution is essentially a summation multiplied with the probabilities of each of the outcomes of distribution minus the log of the probability of the outcome. Okay, so it's exactly this, the expectation under my actions, okay, of log PA prime S prime. I apologize, is I think expectation under A prime, okay? Is a weighted sum. Does this make sense? So since it can decompose over different actions, instead of having this term sit on the S prime, I can take each of those minus log probability of alpha prime given S prime to be here on the black dots. And then my summation goes like this. Instead of just considering the Q, you should also add this minus log P alpha given S. Okay? So we just added the entropy term. All right? So what Bellman diagrams allow us to do is how do we compute a summation of those expected discounted future rewards. All right? That's all they do. Now here, instead of just this reward, which is from the extrinsic task, or if it can be also your intrinsic reward, you also try to maximize the entropy. And these entropy terms sit in the diagram. Once you take an action, each action gives you a log P A prime given S prime, all right? And so then they enter in the equation in this way. So again, you have a Bellman equation, but you call it soft Bellman equation. It's soft because you don't have we call it soft just because we have this entropy term. Okay, we're trying to promote stochastic policies, and compare it with Bellman equation. They look pretty similar. Now, Bellman equations are useful only when the dynamics of the environment are known. This capital T that you see there. When they are not known, what do? We sample, and not only we sample, but the equation becomes an assignment operator, and we have this iterative way of estimating the Q function. You remember, guys? Iterative Bellman operator? Great. So we have our table of states and actions. We start with some Q values, and we iteratively update. And we said that this Bellman operator is a contraction, and that's why if we iteratively apply this Bellman operator, we'll converge somewhere. Okay? Yes?
We're discounting the future entropy of actions?
Yes.
Okay. Is there an intuitive reason for that?
So why we discount?
The future entropy of actions.
Why we discount it? Yes. So it's the same motivation as why we discount the rewards of future time steps. You don't need, if you have an episodic task, that is, for example, 20 time steps long, you don't need to discount. We just add this gamma, because if you don't add this gamma, you have an infinite sum, the sum is going to explode, all right? Okay, so yeah, so I would not put too much emphasis on the gamma. This is just for things not to go to infinity, right? Okay, very nice. So the only thing I'm trying to say here is that things don't change too much from when we didn't have the entropy of the policy in our objective. We just need to add this little thing here. And things still converge if you just do this iterative Q update. This is good. And now you may say, but why they converge? Well, because this update can be seen as, you can rewrite the reward in this way, and then you end the old Bellman operator. So this is the Q update that we just came up with by looking at the diagram. And by rewriting this a little bit, you see that it is the reward and the entropy of the next state. You don't need to go through the equations. We just showed this in the diagram, right? Before decomposing the entropy to actions, you can have the full entropy sitting on the next state. You can add it wherever you like. Okay, you can add this term wherever you like. And you can rewrite the reward in this way. So now you have the reward of the soft reward, let's say. It's like this. And then with this new reward, you can just go and do your old Bellman update operator to estimate the Q function. And because the old Bellman update operator is a contraction, then here again you have a contraction. So things converge, this is good. So we're going to use this. Well, we're going to use it to do some soft version of the policy iteration. So many algorithms that we've seen is a variations of policy iteration, which is what? You have a policy, you estimate its value, and then you update the policy to maximize this value. Okay, that's what we've seen. And here we have the soft version, where the Q is estimated with this soft Bellman operator. And now the interesting thing is how we improve the policy. Here, if you remember, before in deterministic policy we had argmax. Okay, you remember? That we would, for every state, we would look at the next Q, where I'm going to end up, and I choose the action that maximizes the Q of the next time step. You remember the deterministic version? Here, I have this projection. I have this projection using this KL divergence at the distance. I have my policy being, for example, a deep network which is Gaussian. It predicts the mean and the variance, and I'm trying to make it as close as possible in the KL divergence term to this policy that essentially takes the Qs, is an energy-based model where you take the Qs don't need to form a distribution, and you apply the softmax. Okay? So what are Qs? Qs are the values of the different actions. Okay? They don't sum to 1, so you fit them into the softmax operator. And we know what is a softmax operator. It's an operator that takes a vector of scores, here the yi's, puts them in the exponent, and then normalizes with the sum of exponentials. And in this way, now the e to the the resulting normalized scores form a distribution. And this is going to be your policy, all right? And because the policy network that you're training may not be able to exactly match what the softmax will give you, that's why we have KL. I'm just trying to get as close as possible to this output, all right?
What if we have a continuous action?
Yes, that's precisely why we'd use this KL. Because if you had the discrete actions, you don't need anything. You just take this output and you say that's my policy, all right? So there you not need KL. The KL you need exactly because we may have continuous actions. One second. So the Q there, the Q will still be, you still have the Q of the S comma alpha, right? You still can estimate the values, all right? And so you're saying, how do you minimize this? So we're going to go into details. Just give me 1 second to see how this becomes a practical algorithm, okay? So this is the softmax. So we said that the Q converges. Now, the second thing we need to say is, if we use this operator to update our policy, does it improve? And yes, there is a proof in this paper in the appendix. It very much follows how we proved the policy improvement theorem for deterministic policies. You remember we essentially iteratively opened the expectations, and we applied the fact that at every step, the update policy is, the Q is higher than the V of the previous policy. So it's very similar. So that's why we say that this leads to a sequence of policies with monotonically increasing Q values. So far, we've discussed about tabular methods, okay? State and actions. You see there is no functional approximation so far. We assume that we can enumerate all actions and enumerate all states. And now we're going to go to your question. What happens if I have large continuous state spaces, large continuous action spaces, okay? How can we use approximation for this soft policy iteration? Well, we need three things. We need the state value function, the state action value function, and the policy. And remember that the value is related to the Q in this way. So in principle, you can tell me that, did I put it? I'm not sure. So this is exactly the value, the state value function. The sum, I think I put it in one of them to show it to you guys. Yes. So this is exactly the value function, Q minus log P. So if you have approximation for the Q and for the P, in principle, you don't need the value function, okay? However, we are going to explicitly keep also the state value function. We're going to introduce bias, but we're going to trade bias for variance. So how are we going to learn those three approximations? Well, see how simple it is. We have three objectives, one for each. Here is the objective for the state value function. The state value function needs to be similar to the Q minus log of P phi of alpha, okay? And this is exactly the regression objective for which we're going to trade this value function. For now, if you don't mind the policy network, just think about it as something that takes the state as input and predicts a Gaussian, has a mean, and some variance, all right? So you can evaluate P phi of alpha. So this is the target, essentially, that I keep fixed, and I'm trying to make my value for a particular state to go close to that target. All right, this is a standard regression. So we're good here, right? So if I give you policy and Q, you know how to take gradients to fit the state value function. So this is easy. Here is a second objective, also very easy for the Q. Very similar to the Bell-band backup operators that we had before. What is the target? The target is the reward, because I unroll trajectories all the time, right? So I take rewards plus the gamma epsilon of V. This is TD learning, right? So I bootstrap, I use the resulting V that I have estimated, as opposed to using Monte Carlo return. All right? So then what I do, I take gradients, this is my target, and I try to make my Q to approximate R plus gamma V, okay? This is very similar to what we had in actor critic. This is how we trained our critic so far. Nothing has changed. And this V was the baseline, essentially. You remember that we said, okay, it's good to also have a function approximation for the baseline? This is exactly the baseline, the value function, okay? So far, the only thing that has changed from the previous actor critics that we had, I would say, is this, minus log of P phi of alpha, to estimate this, the V. Now let's go to the action. So this is a new objective, indeed. We're trying epsilon of STD means you sample states from your experience buffer. So this is the experience buffer. And you try to make your policy close to the softmax of the Q. All right? That's what you're trying to do. Now let's try to write out this KL. Indeed, is the expectation under the policy of the log of the policy divided by the softmax. You remember how is the KL of P from Q? The expectation under P, log P divided by Q. That's the definition of KL divergence, all right? And you want to take a gradient with respect to phi. Does this so far make sense? I just expanded the KL. This is how the KL looks like. So far we're good. Now, please note that this z theta of sigma t, what is it? Well, it's just a summation, right? It's just a summation, is a big summation over all the actions of exponent of Q. And it is independent of phi. It is independent of phi. Does this make sense? It does not depend on the policy. So what can we do? We can take the log of nominator minus log of the denominator, and because it doesn't depend, it becomes 0. So I can throw it out. So let's throw it out. So are we good so far? So we're good so far, great. Now here's the problem, guys. We try to take a gradient with respect to a parameter, and then we have an expectation, and we had a whole lecture regarding taking derivatives of expectations, right? And we said that if that parameter is inside the expectation, you're good. The gradient just enters the expectation. If that parameter is inside the distribution, you're not in a good shape. But we have learned to do the reparameterization trick. So what does this mean? It's very simple here. It means that it's inside the distribution. Here is what we're trying to estimate. We're going to make our policy a deterministic function of some random variable, which is sampled from a fixed distribution. That definitely, this fixed distribution does not depend on phi or anything like that. All right? So, okay? So this is a stochastic network. You sample alpha, and you take the state, and this enters some deep net, predicts some mu, and some covariance sigma, and you have this, you have a different epsilon for every dimension of the policy. But basically, if you do this reparameterization, now the distribution here is sampled based on this epsilon variable as opposed to your action, and your action is in here, okay? And essentially, now you know how to take the gradient of this expression. So that's how things work, basically. And please, thank you for staying. But basically, I want to show that. And here is the video. Let's see if the video is going to play. Here it's learning. Here is learning this little engine needs to learn to go fast. You see, with very few episodes, this is moving. For other policies, you would have a much, much larger number of episodes here, okay? This is learning to move very, very fast. This method called stochastic actor critic does much better than DDPG. For example, you know DDPG, many of you have implemented it. Look how fast it's running. Now, the other interesting thing is the following. DDPG is very brittle. You sample different random seeds, you have different results. Here, the authors are showing the worst random seed. So it has much less variance over the random seeds if you go with stochastic policies, which is a huge win. And you can see this by the shaded region behind the dark line. So for the orange, which is the stochastic actor, it's much smaller than for, let's say, the DDPG, which is the green, or let's say, what is the other? So yes, it is much smaller variance across the random seeds. Another super beautiful result of those policies that maximize entropy is the following. And I hope you appreciate, we just need a couple of minutes. If you have trained two policies for two different objectives, for example, I want to reach this object, and I want to avoid this obstacle, and you have trained those policies, then you can just achieve the composed policy that both touches the object while avoiding the obstacle without training anything else, just by summing their Q values, okay? And and you can theoretically prove and bound the suboptimality of this composed policy with respect to the policy that you would train under the combined objective. And I have a video here. It seems that we may not have time to show the video, but please go on the slides. And so I'm going to upload the keynote, so maybe you can see the video at home if you wish. Here is one policy that puts this on the left, here is puts on the bottom, and without training anything, just by composing their Qs, okay, and using this combined Q, you just go to the bottom left part of the workspace without training anything else other than the two constituent policies, all right? So this is a big gain of those maximum entropy policies. So thank you very much. We'll stop here because there is a course.